we should keep the midterm for next week. Is that okay?
Yes, but I wanted to ask a question regarding the exam, Professor. So last year we had one.
Let's do that at the end, okay?
Okay, of course.
Yeah. So here's what happens. When we have a linear problem, and if there's only one control variable, we have a bang solution. But if there are more than one control variable, then I know what do you mean by a bang solution? So let me just, it's kind of a linear programming problem. We already talked about this. We have some constraints. The constraints define something called a simplex. In our case, the simplex is like a triangle. Different cases is one. This is a case B and this case A. So for example, if there was only one control variable, the control variable can switch from here to here and back here. That's a bang control. Or if there are more than two control variables, then the feasible space is like a simplex, in this case it's a triangle. Then the control can switch from this point to that point to that point to that point. That's kind of a generalized bang. I call it in the table somewhere. When the Hamiltonian is linear in control variable, I call it a generalized bang. Okay, so that's understood. The question now is how to solve the problem. So first of all, for a problem of this kind, one can solve the simplex or linear programming problem simply by looking at the geometry. So for example, if you look at these areas, if you look at W1 less than 0, W2 less than 0, well, if both are less than 0, then you know that you will set the control U and V at their lowest values, which is 0, 0. So if you see and W1, W2 is less than 0, the control is 0, 0. This is shown in the table here. Control is 0, 0. Likewise, if the control is W1 less than CW and W2 is bigger than 0, then you can see that the control is going to be exactly at this level. Okay. The other thing you want to notice is that C is less than 1. So if you look at the W, you know that the W1 will be less than W2. Right? So we don't need to. So if W2 and W1 is less than 0, both are less than 0, we know that if so given again, if W2 is less than 0, then W1 automatically will be less than 0. So we only need to just say that, right? So what I'm trying to do is in the table, you see I only put W2 less than 0, even though A1 is defined by W1 less than 0 and W2 less than 0. But W2 less than 0 is enough because it automatically implies W1 less than 0. So I minimize the description of the table by W2 less than 0. Similarly, for other cases, here I need both of them because one is less than 0, one is bigger than 0, so you cannot always tell. And so we have a situation where W2 is bigger than 0, so V star equal to 1, W1 is less than 0, so U star equal to 0, and that comes from our simplex geometric solution, which is case A and case B. So I think that we did last time. I just wanted to come back to it to continue. Are there any questions regarding this? Because what we're now, so we have lots of cases. And at any given time, it could be this case or this case or this case. Now we need to find out how do we synthesize this case over time? How did this case occur one after the other? And that is the problem of two-point boundary value problem. Now, it happens that this particular problem is rather nice, and we can solve it using what is called a reverse time construction of the solution. And that's what we're going to do now. And let me define a new time tau, which is nothing but t minus t. And the derivative with respect to tau, I would call it a circle. So y circle is dy d tau, which is nothing but dy dt dt d tau, but dt d tau is minus, so it's minus y dot. And from this point on, until we specify if there is a time somewhere, that time is assumed to be tau, not t, not small t, which is the forward time, tau, which is the backward time. So we assume to be backward time unless otherwise specified. Okay? So lambda t equal to t is lambda tau equal to 0, and that is equal to 0. Notice we are abusing notation here. And abusing xt equal to t, x tau, we assume to be some number alpha a. A means we are in case A, B would be in case B. So, so what's going on? In the Excel example that you solved, we had a 2-point boundary value problem in which the initial value of the x was given and the terminal value of the lambda was given. So what we did? We took the initial value of x as it was, and we guessed the lambda value to be whatever the lambda value we guessed, and then we solve the problem forward in time. And we go all the way to the end, we find that x is whatever it is, and the lambda turns out to be not 0. So what we do, we ask the program to change the guess of lambda so that lambda at the end will become 0. When we do that, x is already there. Lambda is changed to some value so that the exact ending value will be lambda equal to 0 and x whatever it is, because we have no control over x in the sense that we do not have a particular fixed value of x. So whatever x happens to be at that time, we take that value and the 2-point boundary value is solved. So now you see what happens. The 2-point boundary value problem is now in reverse. We now have the lambda value is given to be 0, and we instead guess the value of x at reverse time 0. So it's a problem, it's like an Excel problem, but in a reverse time. Notice, in Excel problem, you could have also solved the problem in the reverse time by simply defining lambda to be 0 at the end and guessing for x. And then solve the differential equation in reverse time and find the value at the beginning, which is reverse time capital T, and make the guess appropriately and solve the problem that way. So either problem, forward time or reverse time, requires that whichever value is given to you, you keep that, and give the value that's not given to you, you guess it. And you guess it until you get to the end, and then you keep guessing it until you get the end points right. Okay, that's what we're going to do. You're going to guess the value to be alpha A, and you're going to solve the problem with reverse time, which now is going to be as if we are solving an equation in beginning from 0 to capital T. So our differential equation now is x circle is this equation, and alpha A is x, value of 0. Remember, I don't put the parenthesis tau here because now tau will be understood to be the time because of this remark that says everything is expressed in reverse time unless otherwise specified. So x circle is given by this, and lambda circle is given by this. We already know these equations. Lambda 0 is 0. This is our guess. And we can start solving. Well, because lambda 0 is 0, this becomes 0. And because we know the W1 and W2 value when lambda 0 is 0. The W1 and W2 are both -1. And when they are both -1, we know from the table or from the graph that U star V star equal to 0. So that is the Hamiltonian maximization problem at time 0. So we set those values at time 0. And we get the X circle to be 0 if you put U and V equal to 0. And lambda circle to be 1 minus rho lambda, because this is 0, so it's 1 minus rho lambda. So we get these two equations. We're going to have different cases. So we're going to first put the case G less than R. You will know later why. Well, it's clear. When G is less than R, 1 is here. And G is less than R, so G by R is less than 1. So you can see our simplex, the solution of the feasible variable, we cannot go to 1. We can only go to G divided by R. The highest value of V can only be G divided by R because 1 is not feasible. That's why we're taking this case first. Second case will be when G by R is bigger than 1, then 1 is here. And we can only go up to 1, not G by R. Because remember, our boundary conditions are 0 V is less than 1, and V is also constrained by this. So we need to take both of these constraints, and both of these constraints are define that corner. Here they define this corner, here they define this corner. So in this case, V less than 1 is superfluous because G by R actually is dominant. And 1 is not important anymore. Basically, what we mean by that is that constraint can be ignored because that constraint is the one that rules the game here and not that one. So we solve this problem. So we're going to keep the control at 0 and to see how far can we go. That means we begin with 0, and in terms of tau, we're going backward, but in terms of tau, we're going forward. And so we are going to solve the problem as tau increases. And because U and V are 0, so X tau will remain constant. And lambda tau, which is 1 minus rho lambda, will become this. That's an easy way to solve that. And we have a solution of this. Notice if W2 is less than 0, then W1 is definitely less than 0. So we will remain in this subcase as long as W2 tau remains negative. Right now it is -1, and it's going to change, and we will see quickly what is going on. First of all, let's see what happens to lambda tau. At tau equal to 0, this is 1, so lambda tau is 0 as we are requiring, because lambda 0 is 0, so that is correct. As tau increases, let's say tau goes to infinity, this becomes 0, and lambda tau becomes 1 divided by rho. So the asymptotic value is 1 divided by rho. So lambda tau is increasing from -1 to 1 divided by rho. It's increasing from -1 to 1 divided by rho, then lambda is going to become 0 somewhere. Right? But let's go to W2. W2 is given by this formula. It is R lambda minus 1. So there is lambda, there is R there, so lambda times R minus 1. So you can see W2 tau, as tau goes to infinity, becomes R by rho minus 1. That's its asymptotic value. But R is bigger than rho. So the asymptotic value of W2 is positive. So it begins from -1, and as tau goes to infinity, it goes to some positive value. So W tau will become 0 somewhere along tau. So we set W tau equal to 0, and we solve this problem, and we find tau 1 equal to be this value. That means that from 0 to tau 1, the control will remain 0. Okay? At least until then. Notice now that our t is given to us. So we are going to have to assume t to be sufficiently large. Let me mention you a question in the exam or anywhere in your reading your papers. We don't always define certain things precisely. We say if lambda is sufficiently large or sufficiently small. That is a mathematical language. Now, of course, in our case, sufficiently large means t is bigger than tau 1. But if I give you a question and I say t is sufficiently large, then you have to sort of mean that I have to have a t so that every case that I want will happen. Because if you assume t to be less than tau 1, then the problem is solved. U star equal to 0, V star equal to 0, and we are done. And if you answer that, if I say t is sufficiently large, and you answer this question, and you say, I'm going to assume t to be smaller than tau 1, and then solve this question, give U star equal to 0, I will say that you will get 0 out of 10, and maybe 1 out of 10. So my t sufficiently large means there has to be cases which will happen, and that's what it means. So let me go to what happens. So this is this is where we started, and we're going that way. And when we're going to go that way, we found that U star equal to 0, V star equal to 0, until this guy tau 1, because we are going this way. So tau equal to 0 and tau equal to tau 1 here. Tau 1 is already given by the formula that we do. When we equate W2 tau 1 equal to 0, we get this formula. So we are up here. So if you assume t to be smaller than tau, then you are somewhere here with your initial value. If you're somewhere with the initial value, which is going to be right here, your graph will look like a straight line going from here to here, which says that I will keep x0 as x0. X0 will remain x0 all the way up to here. U and V will be 0, and the problem is finished. But if that problem is finished, you are not making t sufficiently large. T sufficiently large means t at least has to be somewhere here. So at least you have to get this nice feature that is going to come here as soon as t becomes tau 1, or tau becomes tau 1. So you need to have t. You don't have to be t this large, because nothing new comes in. So t sufficiently large only means t is bigger than tau 1, strictly bigger than tau 1, and that's enough. So we are at tau 1. Not also that if we had assumed r less than rho, which is right here, if r is less than rho, then W2 tau will be asymptotically negative. So it goes from -1 to a value which is asymptotically negative. So there is not going to be any value of tau 1 at which W2 or tau 1 will become 0. So if r is less than rho, every value of capital T will give you U star V star equal to 0. It doesn't matter how large T is. And that makes sense, because if your return on investment is less than what the stockholders want, which is the cost of capital, or the stockholders required return of stockholders required rate of return, then the company should not be in business. So all it means is the company doesn't want to invest anything, doesn't want to raise any extra equity, and just basically works with the capital it has until that capital is no more valuable. ST goes to infinity, it has no value, but you will stay at U star V star equal to 0. In general, what it means in a situation like this is that the company will be liquidated and its asset, which is X0, will be sold in the market, and whatever the proceed of that sale is will be distributed among the stockholders. Remember, this company has no debt. We do not have a debt as a source of financing in this model. It's an optimal equity financing of the model. So the financing is done by either retained earnings, which means whatever you earn, you retain part of it to invest, or you ask new stockholders to give you more money, and that's called new equity. And that's the only way this company raises money. Any questions so far? We are, I don't know if you have not taken introductory finance yet, have you? Or are you taking that course right now? Anyone?
No, Professor.
Or you never taken a course in finance yet?
No.
Oh, sometimes it's a good idea to take this course in the second year. I don't know why everybody takes this course in the first year. But anyway, this kind of assumes that you know some finance, although what we do is more or less understandable. If you know anything, if you ever bought any stock in the market, if you learn anything about the company, this is really, really, really introductory finance. Okay, but if you learn one semester of finance, you will be able to connect what I'm doing much more. In fact, my first paper was published in Journal of Financial and Quantitative Analysis, which was the previous model that I showed you in this chapter. That was one of the first paper I published in my career. So even though I was an OR guy, but I decided to write my first paper in finance. Okay. So we arrive at W2 equal to 0. When W2 equal to 0, W1 is still less than 0, right? We know W1 is strictly less than W2, so W1 is still less than 0. So if you go to the picture, we are now here. No, sorry, we are now here. And notice when W1 is less than 0 and W2 equal to 0, our linear programming problem is W1 is less than 0, so U will be 0. But W2 is equal to 0, so W2 is singular. So V can be anywhere between 0 and 1, or 0 and G by R in this case. So that is the case here. It says that V can be anywhere along this line. And we had a case of singular control before. We worked on a few examples in chapter 2. So we want to find out whether I can manipulate the control in such a way so that W2 can stay 0. That's one way to maintain the singular control. So we want to see whether that is possible. And in most cases, it is not. And then the singular control happens only at one point. And at one point in continuous time doesn't make any difference. And so you can almost ignore it. But that's what we want to see now. So our next situation is whether we can maintain this situation by somehow manipulating the value V over time. Any V star is okay between this and this. So we look at W2 equal to 0. W2 circle 0 means lambda circle 0, and lambda circle 0 means this equation. You notice now, lambda is 1 divided by r at tau 1. So that is its initial value. And that is also that is the value at tau 1. I'm sorry, that's the value at tau 1. So we want to see what happens if you substitute that value to lambda circle. So the lambda circle can only be maintained at 0 if r equal to rho. Right? Because that's all we can do. So lambda is 1 divided by r. 1 divided by r times rho is become rho divided by r. And if r equal to rho, then let me see what's going on. So it's 1 by r, and you have to solve these. You're going to simplify this, and if you simplify this, you'll find that r equal to rho is the only way we can maintain lambda circle equal to 0. And because we have to cancel that one and that minus lambda by rho to make it 0, and the only way to do that is r equal to rho. But we assume r bigger than rho because otherwise the company should be not in business anyway. Nobody wants to invest in a company that earns less than rho. But remember, equal case is an indifference case. It means that I'm indifferent. If I put the money in the company, I will only earn rho. And the rho is my cost of capital, so I can put the money in the savings account, also would give me rho. So that's all what the market is giving. And so there's no reason for me to, I can put in the company or not put in the company, it's just same as a savings account. It is not really a company that's doing anything. So r equal to rho is a kind of a indifferent case, and we don't need to worry too much about it. But it is the case where every solution is optimal. You put the money in there or not put the money in there, it doesn't really make that much difference. It is basically saying, I take the money from my savings account, I put it in a company that gives me the same rate as the savings account. And so you can keep the money in savings account or put the money in the company, it doesn't make any difference. So we assume r bigger than rho for most of the time. And that means lambda circle at tau 1 is actually bigger than 0, and lambda is going to increase. And if lambda is going to increase, we are going to go immediately to this point. So we're going to stay only at a 0 amount of time along this line, and we eventually go right away, immediately. So from there, we more or less immediately go there. And then we want to see whether we can stay there. So that's our next problem. So we go here, we go immediately to case 3. A2 is not sustainable. Only at one point in time you can sustain it. So you can do whatever you want at that point in time. And so we immediately go to A3. A3 W2 is bigger than 0. A3 W2 is strictly bigger than 0. Optimal control in this subcase is 0, and a V star is G by R. And the state and adjoint equations are x dot minus gx. X star 1 is still alpha A because we did not grow x. The asset remained the same. And because there was no retained earnings, everything was going out in dividend. And so money was going out in dividend. There was no external equity. In that case, previous case, not this. And lambda circle is this. And lambda circle tau 1 is bigger than 0. Lambda is increasing at tau 1. from its value 1 by r, and the increase, we will examine now what happens to this increase in two cases. One is rho bigger than g, and one is rho less than equal to g. Remember, g is the growth rate. Let's take the first case first. Rho bigger than g. In this condition, it turns out that if you look at the lambda solution, it will increase, lambda circle will decrease, will become 0 at infinity, and asymptotic value is given by lambda bar. The value of lambda bar is an asymptote to the solution 5.1 starting at 1 by r. And since we are assuming rho bigger than z, so r is bigger than rho is bigger than g. In this case, w bar is r lambda bar minus 1 is given to be this value, which is bigger than 0. So w2 stay bigger than 0 all the way to infinity. So it will certainly stay bigger than 0 all the way to capital T. So we will stay in subcase A3, and the problem is solved. No matter how large the value of T is, we have solved the problem in this case. Let's look at the rho less than equal to G. Lambda tau increases, but it continues to be greater than 0. So we know the subcase will retain, but what happens is the alpha, the subcases remember, and since the optimal value have been found to be independent of alpha A for T sufficiently large, we can sketch the solution for x0. So x0 starts, alpha A is, so what we do now, we can actually solve, so what we're now trying to do in this particular aspect is that we already know the solution. We know the entire solution. The entire solution says, I will, so now this is the forward time. I'm going to talk about forward time now. So in forward time, I start with x0, and I use this control, and I grow at the rate g, and then I come to this value, which is t minus tau 1 in forward time, and I switch the control to 0, 0, and my value of x stays exactly at alpha A. If you look at this picture, if I grow x0 at rate g, then at t minus tau 1, this value of x0 will increase to x0 e to the g t minus tau 1. That's the value it's going to be increased to. And if that value is here, that value will stay all the way up to here. You can see now what is happening in the 2-point boundary value problem. We now know that in order for us, remember the 2-point boundary value problem says that I'm going this way. I took the guess of alpha A for value x, for x, and I took the guess, I did not guess the lambda. Lambda was already 0. The lambda is already 0. And I solved this problem this way. When I solve the problem this way, I find that that I will have some value that depends on alpha A. I will have some value of s at here. And lambda will be whatever the lambda will be, because I don't need any control on lambda. And then I have to change the guess of value alpha A. So I change the guess so that when I solve this problem this way, the value of this asset will come to x0. So that is the guess of alpha A that I would like to have. But that same is saying this is equal to that. So that gives me the value of alpha A. So what I'm trying to do here is alpha A is equal to this, equal to this. So if I chose that value of alpha A, then the 2-point boundary value problem will be exactly, sorry. 2-point value problem will go like this and go like this and will land itself at x0. And so the condition at the beginning will be x equal to x0, and lambda is whatever the lambda is that began from equal to 0 at this time t. So we solve the 2-point boundary value problem. You can see how I can manage the guess. In this case, it is an explicit value that gives me the value of the guess that I need to have to be this. So Excel might try different values of alpha A until it gets to x0. But because we have an explicit formula, we can actually solve it in one just like that. We don't need to do many guesses anymore. But if you do the guess, Excel will have to come to this value of alpha A. It has to come to this value of alpha A in order for it to have this value of x0 at reverse time capital T. Is there any question here? No question? And rho is less than g, lambda tau increases to infinity as tau goes to infinity. And we will see what implication that has when we solve for infinite horizon problems. Because right now it's finite horizon problems, so both cases rho less than g and rho bigger than g are going to be yeah. So this is the rho less than g, this is a rho bigger than z. So both cases we are done. Problem is solved as far as t is finite. When t is infinity, we will go later to deal with that problem. Any question? So now the question, before we go to case B, is to find out what is this value of tau 1. This value of tau 1 that we found, what is the meaning of this value? If you look at this tau 1 like this, you cannot really see the meaning. It is sufficiently complicated formula to tell you what it is. It doesn't really tell you much. But it has to have a meaning. And so we are going to ferret out that meaning right now. And that is the case that we want to look at. We'll also talk about lambda bar later when we go to infinite horizon. But for the time being, let's find out how can we find this tau 1 by some economic reasoning. That's what we mean by interpretation. Is there a way, is there an economic meaning to this tau 1? Well, first of all, notice, here is a point. On this side, U star is 0 here, U star is 0 here. So U star is not going to give us any information. V star is G by R on this side, and V star is 0 on this side. And that gives us some information. That is, at this particular point, I can have this value or that value. I'm indifferent between the two. So at tau 1, I can have either value. Okay? But after tau 1, I must have V star equal to 0. And before tau 1, I must have V star equal to G by R. Notice what's going on. On this side, I am paying dividend in this amount. And I'm keeping 1 minus G by R to invest at this point. And that's why I'm growing. That's why, because I'm investing, I'm growing the rate G. I cannot go all the way to 1 because 1 will grow the company faster than G, and I'm not allowed to grow the company faster than G. Remember, we formulated the problem that there's an upper bound on the rate growth of the company. What I'm now trying to tell you is how you make your papers, research paper, get accepted by journalists in our field. But journalists in our field want you to tell more about tau 1. They want to talk to you about things, not just math, but what is the meaning of all the math that you've done so far? And can you say something more? And that's what you need to do. So that's what we're trying to do now. So we have a point of tau 1 where I'm indifferent between retaining earnings and not retaining earnings. Here I invest, here I don't invest. I'm indifferent between investing and not investing. I'm indifferent between retaining earnings and not retaining earnings. Retain earnings means investment. So we need to find out what happens if I invest $1 here. Remember, at this point, I can invest $1. After this, I cannot. Before this, I have to. But here I can invest $1. Exactly at this point. And if I invest $1, what am I going to get? Well, if I invest $1 at this point, I'm only going to get dividend, right? But the company is not growing. It's not earning any external equity. It is going to stay exactly at this value x0 e to the gt minus tau 1, which is now, you can call it alpha a if you want, if you already set the value of alpha a. Then it's going to give me dividend all the way from here up to here. Remember, if I invest $1, how much do I expect? I expect this company to give me dividend that will compensate for me for my investment. And I am requiring to give you to give me, or the company to give me, at least my cost of capital, which is rho. Okay. So the optimal control before time t minus tau 1 is u star 0, v star g by r, and x star t is this. And after time t minus tau 1, u star is 0, v star is 0, and x star t equal to this, all the way up to t. Lambda t is also like this. And from t minus tau 1, I can begin with the lambda t minus tau 1 and continue all the way. And we have a solution for lambda t all the way to capital T. Yeah, I only give you up to t minus tau 1. That's all I need for this. The switching time, I already told you, has this interpretation. It's an indifference between paying dividend and, I mean, a point of interest between retaining earnings or paying dividend out of earnings. So the firm retained $1 of earnings at t minus tau 1. Since this is the last time any of the earnings invested will be worthwhile, it's obvious all earnings will be paid out. And all the earnings will be paid out, then if I invest $1, the earning will be R, the rate of R, and it's going to be discounted by rate rho. And so the present value of that earnings that I earn between, so in this, if I invest $1, the present value of all the earnings that I will do all the way from here to capital T at this point, the present value of this point will be exactly this. This is in t minus tau $1. That means I'm making a calculation at this point. If I had $1 and I put that dollar in the company, what would I get? Well, I would get exactly R all the way up to here, and I'm going to take the present value of that earnings to find out what the present value is at this point, and that present value must be equal to $1. So that's what I have right now. So whatever I get has to be equal to $1 at that time. So that has to be equal to $1. So I equate that to $1, and you will see that if you equate that to $1, you will get exactly this formula. Exactly 5.35. So the 5.35 economically means what it means as 5.49. If you equate that to $1, you get tau 1. So tau 1 is the last, t minus tau 1 is the last time at which I should be retaining earnings. After that, the company should not retain earnings. So we conclude that enough earnings must be retained so as to make the firm go exponentially at rate G until this time. Enough means G by R in this case. Enough has a meaning now. You see, the mathematics has all sorts of stuff here. Instead of saying G by R, I say enough. And enough means it says a little bit more than just G by R. It says something in English which says I cannot do more, but I should not do less either. So I do exactly what is required, which is G by R. So at this time, all of the earnings are paid out and the firm stops growing. Since G is less than R, the growth in the first part of the solution can be financed entirely from retained earnings. Thus, there is no need to have expensive external equity financing. Remember, external equity financing is expensive. I need to pay money to the investment broker, C, 1 minus C, I have to pay. The latter will not be true in case B, which we will now discuss. So, any question in case A? We have solved the problem completely. We have solved the 2-point boundary value problem completely. We have found the solution and presented that in this graph. And we have given the entire solution. And we have given a very concrete meaning of what the meaning of this switching point tau 1, t minus tau 1 is. Notice now, this is the t. It's sufficiently large. But suppose my beginning point was here. Well, the beginning point was here. I already told you that x0 will be here. And my solution will just simply go from here to here, just like that. Finished. What if my beginning point is here? Well, if the beginning point here is x0 will then exactly going to be here at this point. This is my initial value, initial time. And starting from this time, I will have a curve which is going to be parallel to go like this and go like that. It'll start from x0. It will grow all the way up to here, and then it'll all the way up to here. So if I was to begin here with this x0, I will go like this, and I will go like this, and alpha A that I will need will be exactly here, not there. It'll be here because x0 is x0 here. On the other hand, if I begin with this x0 at this point, whatever that is, then I can keep this curve if I start from here. So I've solved the problem for every t except infinity, which we'll talk about later. B. Now G by R is bigger than 1. So the constraint V less than 1 is relevant. And instead of just 3 cases, we now have 5 cases. So we will go back to the picture and we'll see these 5 cases. Case 1, case 2, case 3, case 4. No, case 1 and case 2 and case 3 and 4. Let's just go to the table here. So we have B1, which is 1, and B2, which is a singular case, and then B3, which is not the singular case. then B4, which is a singular case, and then B5, which is not the singular case. So what I'm trying to do is to take this point, and this point. Those are the three cases, and that's, no, sorry, this point, and this point, and this point. Oh, B7 never happens. This point, and there are two singular cases. That one never happens. We ruled out before. So those are the cases. And we start with B1. Okay? And the book is now, at one time I had these in a different order. Now I made them to A1, A2, A3. By the way, I got my book this week, this week. My fourth edition just came a few days ago. Until then, I only had a print copy because the Springer forgot to. They told me they'll mail it to me right away, but they didn't, and so I asked them, and so it came a couple of days ago. So B1, exactly as before. So there's nothing to be discussed. There's no change here. B2 is exactly same as before. But remember, instead of G by R, we now have a 1 here. So that's a difference, but it's not going to change anything else. So B1 and B2, that means the singular control still cannot be maintained. And so we will go immediately to case B3. So B3 is now different. Now let's go and see what is happening with A3 and B3. So A3, A2, so we were here. Then we found that there's nothing going on there. We can only stay at one point in time, and then we got here and we were done. So that was our entire solution. Now, in this case, we were here. Then we found that we can be on this point, on this line only for one point in time, and then we are here. So initially we were there and to see what's going on next, and this doesn't work, so we were finished. Here we are here, and we want to find out what's going on, and we'll see that now we will go to this singular control, and then we're going to come here, and then we'll finish. So there are two more cases to be considered, but the difference between that point and that point is the value. Now our maximum value is 1. Before, the maximum value was G by R. So now it is 1. So that difference. So if you look at A3, this V star is G by R. Now we go to B3. This is the same. This will be 1. And that changes the calculation. Now we want to see what happens after B2. Okay? And we'll find that we get to subcase B3. No, I was already here. I'm now here, B3. So let's see what happens. At this point, this is our situation. We want to see if we can maintain this. And X circle is minus Rx. And X star 1 is alpha B. And alpha B is a parameter to be determined. Lambda circle is that one, and lambda tau 1 is 1 divided by R. So we begin with 1 by R, and we can solve the problem for tau bigger than tau 1. So we have the value of lambda tau for tau bigger than tau 1. And because we have value lambda tau, we can compute the value W2 tau. So as lambda increases, W1 increases, becomes 0 at time tau 2, defined by W1 tau 2. Notice W1, this is bigger than 0, this is less than 0, and we want to find out what's happening to these quantities. So W1 is CR lambda minus 1. So that is CR, there is R, there is lambda, and at tau 2 it is equal to 0. So we get a value tau 2. And at tau 2, the firm switches the case before. So we know that this cannot be maintained. Again, where are we doing there? Yeah, this singular control cannot be maintained as before. It's again require um, the same analysis, and so we didn't have to um, as before. The singular case cannot be maintained for a finite time because of r bigger than rho. If r equal to rho, it can be maintained, but that we already ruled out. Okay, so we are now saying at tau 2, and this is the value of tau 2. And at tau 2, the firm switches to case B4, and we will see that this B4 also want to see whether the B4 can be maintained. And here's a singular control. V star is 1. To maintain this single control over finite time, we must keep W1 equal to 0. And this must we have to have the W circle equal to 0. For that means lambda circle tau 2 has to be equal to 0. And we put the lambda circle tau, put the value, and we can find out that again, r by rho is required for us to be indifferent. So what we are now saying is to maintain a control no, I'm sorry. I have to go here. We're now saying to maintain that singular control and stay somewhere along this line, I need to manipulate the control U in such a way that I can keep the W1 as 0. And that I cannot do unless r equal to rho. So I cannot really spend any more time on this line as just except one instant. And then I eventually go to B5. And we will see that B5 will be maintained forever. So that's how this case will be solved. And we will go to that analysis. But before I go to analysis, it might be interesting to see what is going on in a picture. So the picture looks like this. So B1 was the same as before. B3 is similar to before because the only difference was that there the V star was G by R. Here it is 1. So the firm is growing at the rate R, not at rate G, because earnings are at the rate R. So this growth rate is at R, not G. Whereas in the previous case, A3, the growth rate was at G. So we are growing not the maximum rate, but we are allowed to grow at the maximum rate, but we need external equity to do that. And external equity is expensive. And the model says that I should not be able to use external equity until T minus tau 2. This way. Until tau 2, I'm sorry, until tau 2 this way. And then I come to this point, as you can see what's going on here, it says that I will still retain earnings, all of it, but that only will give me the rate growth of R. But now I eat a little bit more money from outside investors to make up for this difference. And together, I can grow at the rate G. So what is it trying to say? It says that if I have a beginning investment here, then and if my T is sufficiently large, now sufficiently large means it's bigger than tau 2, not bigger than tau 1, because bigger than tau 1 does not give you this richness here. We need to have this case and this case, and then there's no more case. So we need to have at least T sufficiently large. So T at least had to be bigger than tau 2. And if t is bigger than tau 2, then some part of the time, I will grow at rate g. I will use external equity. And then at some point, I will not use external equity, only grow at rate r, still keep retained earnings. And at this tau 1, it is the same as case A. I don't need any retained earnings. I will pay full dividend, no more investment, and the company will stay along a straight line all the way up to here. Notice, if I give you this solution, this solution, this solution, then I can also go to x0 and grow that at rate g to come to this point, then grow this guy at rate r to come to this point. You see, growing at rate g, so it's e to the gt minus tau 2. And then I have this value, and this value grows at the rate r from tau to tau 1, tau 2, from this time to this time. Then that's r times tau 2 minus r1. So that is the value I get here. You notice I have solved the problem, and I have connected x0 to alpha b. So I can tell you exactly the right value of alpha b is exactly this value. So I can easily compute alpha b as this value, and then the 2-point boundary value is completely solved. Otherwise, I can either do guessing and do Excel, or I can do this explicit formula, which beats guessing altogether. But that's only happens in in some cases, not always. So now let's go to this point to say that we can maintain this case forever all the way. Okay, so we will go there. So we already found the value tau 2, which, by the way, tau 2 is tau 1 plus this. And again, the meaning of this, economic meaning of this, has to be obtained. And the economic meaning of is somewhat more complicated. But we will see, we can still get to it. So I already switched to B5. And we see that lambda circle is bigger than 0, which implies lambda is increasing and W1 is increasing. And so tau 2 plus switches subcase to B5. B5, I have a W1 bigger than or equal to 0. The optimal control is U star and V star. That means full retained earnings and a little bit of external equity to keep the growth rate G, which is I'm allowed to. So the firm is growing at the rate G, which in the other side is it's opposite of growing because we are in a reverse time. And lambda circle is given by this, so we can solve this problem starting from tau 2. And we can see the lambda circle is increasing. Lambda tau is increasing at tau 2 from its value. We have G bigger than R in case B, which together with R by rho means G is bigger than rho. This implies the second term on the right-hand side of 5.62 is increasing. So look at 5.62, the second time. So we need to have the values of R and G and rho to see where they line up in order to get this case. So we have this case already, so we can say it's increasing. The second term dominates the first term from tau bigger than tau 2. Since lambda tau 2 is 1 by RC bigger than 0, R is bigger than rho, G is bigger than R. It's a lot of stuff. But G minus rho is then bigger than G minus R, so bigger than 0. So to conclude, lambda circle bigger than 0, we need to look at all of that. And the firm continues to stay in subcase B. Note the lambda tau in case B increases without bound. It goes all the way to infinity. And that, again, has implication for infinite horizon problems. For finite time, it will be finite regardless of how fast it grows. And so there is no issue. So the next thing we want to do is find out what is the meaning of this guy. tau 2. It's now, if you look at this point, we need to see the following. Here, I raise some external equity. Here, I don't raise any external equity. So this point is indifferent point between raising external equity and not raising external equity. So what I want to find out is, what if I put $1 of external equity at this point in time? Suppose I get one stockholder, outside stockholder, a new stockholder, who gives $1 to this company at this point in time. What happens to that dollar? Before, every stockholder will give money. After, no stockholder will give money. At this point, it's indifferent. So I can find a stockholder who will give me money, and I can analyze what happens to that $1. Well, look what happens to that $1. That $1, from this point to this point, there's no external equity, so there's no new stockholders, only that $1. And all the earnings is being retained, so there is no dividend to be paid. So this guy, that $1 guy, the new guy, is not getting any dividend all the way up to here. At which point his dollar has grown to some value. We can find out what that value is. And at this point, there is dividend. So this guy who put $1 here will only get the dividend from here to here. No dividend here. We need to find out what these dividends are, how much of the dividend he gets it. Then you have to present value those dividends to see what happens. All of that calculation has to be made in order for me to find out what happens to that dollar. By the way, over the years since I published this paper in 1978, again in a Journal of Financial and Quantitative Analysis, I have those explanations in that paper. I have not looked at that paper, I don't think, for years now. But as I write this book, and it's now in the 4th edition, you will see over these 4 editions how the explanation of this tau 2 has improved in terms of exposition. I have given more things to explain it better. In my mind, the explanation was there in 78. I knew the exact explanation, but how to explain that to the audience, to the readers, require a different kind of skill. And over the years, I have improved that exposition. And what you see now is the improved exposition of the tau 2, better than if you read that paper in 78. Okay, so let's go with that. The firm issues $1 worth of stock at time t minus tau 2. That means it found one stockholder, and that stockholder gave the firm $1. But when it gave the firm $1, 1 minus C went to the broker. The company only got C dollar. C is strictly less than 1. So the company only got C dollar, not $1. But the stockholder paid $1. So the stockholder is expecting the return on that $1. Okay? The broker gets his commission whichever way, and they have their own calculation of how much to charge. And company then decides to, go through this broker or not. But we have all decided, and that $1 has been invested, and the company got C dollar as a proceed from that $1, and that proceed is going to be earning some money. Well, there's no dividend, as we say, from t minus tau to t minus tau 1, and the firm grows at the rate R. So the investment of C dollar grows into C times e to the R times tau minus tau 1. Look at the picture. If I got C dollar, if the company got C dollar here, The stockholder paid $1, the new guy, but company got C. That C grew into, because it's invested, no dividend is paid out. All earnings that is accumulating to C is invested. So the C is growing at rate R. Every dollar in the company is going at rate R, so does C. So C will become C R times tau minus tau. This is the amount of time the C has, and it grows at the rate R, so that this compounding rate of R gives you this amount of dollar at time t minus tau 1. So this is first calculation. We first have to go from here to here, because we cannot just do this just like that. We need to find out all the consequences of what happens to this C dollar all the way to the end, and then evaluate that value and see how that compares with $1. So the point of the buyer of the stock at t minus tau 2, no dividend is paid, and the stockholder rate of return is rho. So the firm's future dividend obligation at t minus tau 1 is C e to the rho tau minus 1 in t minus tau $1. Okay? And that has to be equal to that quantity. Anyone, any question now? So what am I trying to say here? The buyer expects rho. So the buyer's dividend, the dividend obligation that the buyer wants at t minus tau 1 is this amount. So for the point of the buyer of stock at time t minus tau 2, since no dividend is paid as until t minus tau 1, stockholder required rate is 0. So the firm's future dividend obligation at time t minus tau 1 is this much. So what I'm trying to say is that dollar obligation has increased the obligation at this point by the rate rho. Okay. And that has to be equal to this. And if you equate those two guys, you will get exactly this formula. If you any question, but there's some more comments, so let's continue. The firm is marginally indifferent between investing any costless earnings at time t minus tau 1 or paying it all out as dividend. This is tau 1. Return earning is costless. This also means that the firm will be indifferent between having the new available capital of this amount as a result of issuing $1 worth of stock at this amount. So the firm is also indifferent between this available capital at t minus tau 1 or $1 worth of capital at time t minus tau 2. It's another way to look at it. Thus, we can conclude that the firm is indifferent between issuing $1 worth of stock at time t minus tau 2 or not issuing it. This means that before time tau t minus tau 2, it pays to issue stock as large a rate as feasible, and after time it doesn't. As large a rate is again an English language for whatever the rate that's feasible to give the growth rate to this company to G. Because that's feasible. No rate beyond G is feasible. You can compute that rate to give you the G rate growth. This is the way to express that. So we now conclude that all the earnings must be retained from this t minus tau to t minus tau 1. Because R is bigger than rho, it follows the excess return. So this is another calculation that we have. Because R is bigger than rho, we need to compensate for the flotation cost by earning more. But R is more than rho, so the company is earning more than rho. And so while it lost the 1 minus C to the broker, the C that it gets can earn more than rho because it's earning at rate R. So the it has to compensate for the cost that is gone. It's gone from the company's hand and from the stockholder's hand. So because it follows the excess return on the proceeds C from the new stock is this amount. Because this is the amount it's earning, this is the amount it must, from the stockholder's point of view. And so we know that that must be equal to the money that we gave to the brokerage house. So another way to look at it is that if you equate that excess return to 1 minus C, you'll also get the same formula. So we have actually provided 2 or 3 ways to find this meaning. One equation also gives you tau 2. Another equation is this one, which gives you tau 2. And there was another equation somewhere which also gives you tau 2. So we now have the meanings of the value. Remark 5.6, instead of reading, it's better to just go to the picture and just say that if I begin here, then I will take the x0 here, and I will go like this and go like this, and I will go a parallel route and draw a chart. So whenever I have an x0, I will grow for a while until t minus tau 2. And then whatever the t is given to me, I will go up to this point. Then I will grow this rate at g, then rate r, then this. So I can find the solution for any t that's given to me. If t is only from here to here, then I will not get this portion at all. If t is from here to there, I'll get all 3 portions. If t is here, I will not get these 2 portions. So for every value of t, I also can solve the problem B, case B. Let's finish the infinite horizon solution, and then we'll switch to chapter 6. The infinite horizon solution, we know that transversality condition is given by this. This is the standard. This is the it's the current value lambda t, and it's the present value of that has to go to 0 and t goes to infinity. This condition may longer be necessary. We know that. We had some example in an exercise somewhere, and we also talked about it. But it is sufficient. We had a sufficiency theorem that goes through for t going to infinity. So let's take the different cases of what happens. Case A. Rho bigger than g first. T goes to infinity. We can just let everything go to infinity, and everything works here. This goes, this goes, this goes, and lambda t eventually goes to lambda bar, and t equal to 0. So lambda t is basically goes to lambda bar, and we have solved the problem. Clearly, lambda t satisfies this, and so the solution can be maintained, and basically we are done. What we're trying to do is the following. So note that the assumption rho bigger than g together with the overall assumption rho less than r gives us g less than r. So 1 minus v star is bigger than 0, which means the constant fractional earning is being paid as dividends. Remember, even though in this case we are paying dividends, we are retaining earnings, but we are not retaining all the earnings. We are not allowed to, because the company can only grow at the rate g. And because rho is bigger than g, we are still able to give dividend. And notice that this lambda bar, which is a constant, it actually, Myron Gordon was a professor at University of Toronto when I was a young professor. And Gordon was a senior finance professor who at one time was the president of American Finance Association. And he had moved from Rochester to Toronto. And he did his PhD at Harvard. And at that time, there wasn't that much mathematics. In fact, Gordon was one of the more of a mathematical guy at his time, which was probably 1950 or a little bit earlier than that. And he created a classic formula that is called Gordon's formula. The Gordon's formula is like this. A unit increase in earning. So obviously, a unit increase in earning will mean an increase of 1 minus G bar units of dividend. And so 1 minus G bar is this a dividend. And the dividend is growing at the rate G and being discounted at rate rho. So Gordon said that if a stock is earning a dividend which is growing at rate G and being discounted at rate R, then that divided by that is the value of that stock. That means the value of the stock is the present value of the dividend it earns from all the way from here to infinity. That was Gordon's formula. Gordon's formula was basically you sum a geometric series which is growing at rate G. If you sum a geometric series growing at rate G and being discounted at rate rho, then instead of 1 minus rho, you will have to have rho minus G. Okay? Instead of rho, if there's no growth, then the capital $1 dividend all the way to infinity, its capitalized value is 1 divided by rho. That's the sum of the series. And if it's growing at rate G, then its capital value is 1 divided by rho minus G. But it's 1 minus G by R because only part of the dividend is given. And so this formula is a Gordon's formula for my problem here. He did not solve this problem, but he basically said that's what happens for the present value of the dividend and the price of the stock at the present value of the dividend. Then the Gordon was supplanted by Modigliani, who got a Nobel Prize for their theory called Modigliani theory, and they showed that the present value of the firm is obtained by a cash flow approach. And you will learn all these things when you go to finance course. And so there was a fight between Gordon and Modigliani in the journals. In the end, I think that both were right in some sense, but Modigliani won the day because the Gordon's view was that the dividend carry information, and Modigliani's view was that they don't. If they carry information, Gordon's right. If they don't, Modigliani is right. Anyway, all of that is not something I want to say right now, but I do want to tell you that Modigliani were at Carnegie Mellon, although they left before I went there, and I worked on their problem of Modigliani theory, and I wrote a bunch of papers, which are all published. And one day I do want to put all of those together into a book on extension of Modigliani, and it will be basically all my papers in there. 6 or 7 of those papers are all published somewhere. Okay, so what we're now trying to do is giving you something which is unusual usually, and I want to alert you to this kind of situation that may arise. For rho less than G, so this is the case when we have the situation where rho is bigger than G. So we're trying to give all of those cases. For rho less than G, lambda t does not satisfy 5.65, which is the condition, transversality condition, because it is growing all the way to infinity. And objective function can be made infinite. So for example, any control policy with with earnings growing as rate Q, where Q is between rho and G, coupled with a partial dividend payout, will give you infinite value of the firm. It's like this. Take E to minus rho t, 1 minus U star minus V star, and we can assume U star to be 0 and V star to be Q by R, then this will go to infinity. because rho is less than Q, and Q is going faster than Q. So any dividend that grows faster than rho will give you infinite value of the firm. So also, okay, Q may be chosen, but there are many solutions. There are many different Q that will give you infinity. So what we're now saying is that the problem is that means the finite horizon solution is still not pathological. But now we go, so to conclude, we know that the limiting solution is an optimal solution. However, there are many optimal solutions because lots of different optimal solutions, they all give you the value infinity, and there is really no way to choose among them, at least in the setting that we have. That requires a different kind of setting, and that is beyond the scope of this paper or this book and beyond the scope of this course. But all I'm saying is that the firm becomes infinite for many different policies, and there's no way to choose between this infinity and that infinity at this point in time. But when G by R, there are different problems happen. So now the limit of finite horizon solution is to grow at the maximum allowable rate, because now I can allow maximum rate. I don't have to pay any dividend because V equal to 1. And so if you take the limit, there are no dividends, stockholders gets nothing. So the value of the firm in the point of the stockholder is 0 if you take the dividend into account, right? So I call that solution pessimal. That means an optimal solution, which you take the limit, becomes the worst possible solution ever. When we wrote this word pessimal, when Jerry and I wrote this word, we thought we invented a new word. But we really didn't invent a new word, because when we finally checked, it turned out that that word has been used all the way back by Voltaire's critics in 1769 or something. And it has a meaning in the worst possible case of the world. And there are a lot of philosophical ideas attached to this business. But that's not what I'm going to talk about, right? So let me just go and tell you what is going on. So if you take here's my picture. If you take this solution, and if I let t go to infinity, this is my finite horizon solution. Let's take t go to infinity. If I take t go to infinity, the limiting solution is basically this. That one never happens because there is no such thing as infinity minus tau 1, right? Infinity minus tau 1 is infinity. So this portion never happens. But in this portion, the people are getting dividend. All the way they're getting dividend. So in one case, the value is finite because rho is bigger than G. In another case, the value is infinite because rho is less than G. But the limit is not pathological in the sense that the optimal solution is still okay, although there may be any other solution which give you the same infinity in the second part of that. So this is fine. But let's see what happens here. Now, if I take limit of this solution, then that disappears. Because infinity minus tau 1 is still infinity, phi minus tau 2 is still infinity. So the optimal solution, not optimal solution, the limiting solution is this going this way, all the way to infinity. But in this solution, no dividend is ever paid. And stockholders are giving you money. The outside stockholders are giving you money. And no dividend is ever paid. So the firm has value in the Miller-Modigliani sense of infinity. Because it's growing all the way to infinity, no dividend is ever paid, and it is what is called the growth company in finance, where people are putting money. Remember, some of the technology companies were growing. They were not paying any dividend because they were growing so fast. There was no sense to pay dividend. Retained earnings was going to be invested again and again, and that was in the interest of the stockholder. But the stockholders are expecting dividends someday. But if T is finite, they will get that because the company will be sold and the money will be huge and that will be divided among the stockholders. But if the company never pays the dividend all the way to infinity, then you don't know what's going to happen at infinity. Nobody is going to live all the way to infinity anyway. And so there is this pathology that the company is becoming an infinite sink and is not giving dividend anywhere, ever, 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 ever. So the Miller Modigliani also did not do a good job there. They said, okay, someday the company will give dividend. But which someday? Because their model was also finite, no, deterministic. Deterministic, you have to say which day you pay the dividend. You cannot say someday. It's not stochastic. So I had to also extend their model to stochastic firms as well. Though I think maybe some of that is cited in this book. At least one paper may be cited in this book, my MM papers, but they are available. So I want to give you this idea. I want to give you this idea that suppose I have an initial optimal solution of a finite horizon firm. And let's solve the problem of infinite horizon as well. And let's say optimal solution of the infinite horizon is given by these formulas. We already know that this is infinity in case B. Define an infinite horizon U infinity by extending these guys. So I'm now taking the limit of these guys. This is the optimal solution of infinite horizon. This is not the limit. This is the limit which I call this. So that's the limit of the solution, not the limit of the objective function. We now see that in our model, the limit of the objective function is infinity. But the objective function of the limit is 0. And that is, in mathematical terms, say that this mapping of J is not a closed mapping. I'm not going to talk more about that, but I do want to go a little bit more. I do tell you why that's happening, because nobody's getting, so what is happening? Happening is nobody's getting any dividend on that solution, which called the limit of the solution. But the objective function limit is going to infinity. And the firm is becoming infinite sink. The way to break this mapping and make it a closed mapping is like this. That means we assume that a finite horizon firm will be liquidated at capital T. And that liquidation value is B times this for some B. We do not know. I mean, that is always a question in finite horizon firm as to how you value the T, capital T. But let's assume that we value it simply this way. Now what happens is the new value, the JBUV, is a closed mapping because that value is going to come to the stockholder at infinity. And that is infinity. So while this is 0, this is where the stockholders cover their value back at infinity. But if I don't put that value, then there is no value there, and the value at infinity is 0, and this is 0, and so the stockholders never recover any dividend ever. Here, they recover not the dividend, but the liquidation value of the firm. So now JB is a closed mapping because it is infinity, and the limit of the solution is also infinity because the limit of the solution includes this term. Here's an example now. X0 is 1,000 per month. T is 60. R is 15%. Rho is 10%. G is 5%. C is 2%. I mean, the broker commission is 2%. And we assume, so G is less than R here. The problem is case A. Tau 1 is given by 11 months approximately. The optimal control is 0 up to 49, and 0 and 1/3 up to 49, and 0, 0 after 49. Xt grows like this up to 49 and then stays exactly at this value. The value of the objective function is 0 to 49, this one, and from 49 to 60, that one, because we have 1 minus u minus v star. So we can put those values there and we get this. If you now put t equal to infinity, then the optimal solution is this. And remember now, there is no tau 1 anymore. So the optimal solution is all the way from 0 to infinity this. So the optimal solution is 0, 1/3, all the way to infinity. There is no tau 1. And now you can integrate all the way this quantity from 0 to infinity, and you will see that the value is now that much. So a finite horizon firm gives you that much. Infinite horizon gives you that much. And that's coming because there is some dividend all the way to infinity. And it is more than a finite horizon. The company is still better than finite horizon firm in terms of the stockholder values. And so the stockholders are better off because they're getting dividends. In B, they don't. So that's what happens. Okay, so if there are no, we are finished with chapter 5. If you have questions, you can ask me right now. Otherwise, we're going to take a break and we will come back to chapter 6. So I'm going to go to chapter 6. I suppose I have to stop the thing again, stop sharing, and then share the new one. Go back here and share the yeah. Okay, let's take a break and we'll come back in 5 minutes or so. Okay, is everyone back?
Yes.
Yes, Professor. Yeah.
Mohammed, you're here. Jarui.
Yes, yes.
Okay, Kisha. And Chusha. Chusha, right? Pramit.
Yes, yes, Professor. I'm here.
Okay. Let me. Chapter 6 is a production and inventory chapter. This is the area that we are in, but I scheduled the chapter 6 after 5 because 5 in some sense is simpler, and also it was the first um, research papers that I had written, and after that I actually wrote papers on production and inventory. And the one that I'm going to present is a paper that was published in Management Science. So I'm going to start with that. The classical EOQ, I have a little bit of an issue because I don't actually know what you guys have done. Now, the EOQ model is something that we do in operations management at the very, very beginning. So let me ask you, does anyone not know what an EOQ model is? Only tell me the ones, only somebody who doesn't know, tell me that they don't know. Okay, so everybody knows EOQ model. So you're taking some courses in OM, or you have taken those courses before you came here. This model was the earliest model. It, by the way, maximizes something called long-run average cost. It's not a discounted problem. And remember, I told you something about the infinite horizon problem where you have lots of infinities and you don't know which one is a better solution among them. Well, the alternative of that is that when you have a problem like that, you solve the problem as a long-run average cost problem, which is a more complicated setup in mathematics. And if you look at my set of my books, there's one book that is basically devoted to long-run average cost problems in manufacturing. EOQ is a special example of a long-run average cost problem, but it is a simple example. The dynamic version of EOQ model was called lot size problem. Dynamic was a lot size problem by Wagner Witt in 1958. And a dynamic production planning model, which is the one that I'm going to be close to, it's called the HMMS model. Holt, Modigliani, Muth, and Simon are the 4 people here. Modigliani received a Nobel Prize in Economics. Simon received the Nobel Prize in Economics. And Muth was a guy who actually started the field of rational expectations but never won the Nobel Prize. The Nobel Prize was won by Bob Lucas, also at Carnegie Mellon, on the rational expectations. So, no, this is not correct. How come 1910 is showing up here? Yeah, this should be 1960. No, it cannot be 1910. I'll have to check that. And they use calculus of variance to solve it. And remember, we connected calculus of variation with optimal control in chapter 1, at least by some words. And the section 6.1 is a model by Thompson and Sethi. Thompson was my PhD advisor. one of the two PhD advisors. And that was similar to Holt, Modigliani, Muth-Simon model, but we solve this using optimal control. Section 6.2 is a retrading model of Ejiri and Thompson, which was an accounting professor here named Yuji Ejiri. Both of them are no more, and that's covered in chapter 6.2. I also worked on retrading model after their model, but what I cover is morally their model, except some examples later. These problems are currently in my mind because I just finished a long survey on SS policy model, which is kind of related to these guys. And that is a 40, 50-page survey that will be forthcoming in POM. I have not sent it to anybody yet because it is 99% finished and it's waiting to be finished in a week or two. Then I can put an SSRN. Okay. So the production inventory system is to manage fluctuations in consumer demand for their product. Consists of manufacturing plants, finished goods, stored products. Once a product is made and put into inventory, it incurs inventory holding costs of two kinds. One is called cost of physically storing the product, insuring, etc., as a holding cost. And the other one is opportunity cost of having the firm's money tied up in capital, capital tied up in inventory. So there are some costs of holding inventory, then there are benefits of holding inventory in the sense that when there's a demand due, you immediately meet the demand. If not, then you incur some cost called lost sales cost or cost of backlogging. And the excess production during the low demand period can be stored in the warehouse, so it will be available for sale during the high demand period. And if you produce to satisfy a demand that fluctuates over time, like the seasonal demand, then people would call they want to do what is called a production smoothing. That means that you want to produce and you don't want to change production so rapidly because changing production costs money. We don't get into that, but there are papers on production smoothing where there's a cost of changing the production, and that will give you the production, more even production than production changing like that. So this is the whole Modigliani-Muth-Simon model in optimal control formulation. IT is the inventory level at time t, PT is the production rate at time t, ST is the exogenously given sales rate at time t. We assume this to be bounded and differentiable in time. T is the length of planning period. I don't want to call it a planning horizon because that horizon term gets confused in this because we'll have another meaning for the horizon. I hat is the inventory goal level, means this is the ideal level of inventory that I like to have. I0 is the initial inventory level. P hat is the production goal level, which is the optimal level of production from the production point of view that you like to have. H is the inventory holding cost. C is the production cost coefficient, and rho is the constant negative discount rate, rho bigger than or equal to 0. If it's finite horizon, we can have bigger than or equal to 0. If it's infinite horizon, we must have strictly bigger than 0. It's a deterministic problem. So I dot is production minus demand and initial inventory I0. So this is just the stock flow equation, accounting bookkeeping equation, which says inventory at time increases by production and decreases by sales rate. The objective function is a la HMMS model. It says I like the inventory to be as close to I hat as possible. So anything beyond I hat this way or that way will cost me money according to this formula. And I like to be production as close to P hat as possible, and any deviation from production will cost me money, and that is given by this. And I discount this whole thing, and I integrate over 0 to T, and I minimize. I minimize over P. P is my decision variable. So the smoothing here comes not because there is a change in the cost of production, but there is an ideal production level, and any deviation from production is expensive. And this being quadratic, it means that the cost is increases as the deviation increases. Cost increases more than linearly as deviation increases. And so you like to be close to P hat, and that gives you a smoothing as well. So you can even call this as a production smoothing model because of the way the cost is defined. I put 2 only because I put h by 2 only because when I take the derivative of this, I will get a 2, and I want a 2 and 2 cancel out, so there is no fractions going all over the place. But that's that's just a parameter. It doesn't really make that much difference. Hamiltonian is straightforward. Using the derivative with respect to P to maximize the Hamiltonian gives you P star equal to this. But now notice there's a problem. We cannot usually allow P to be negative. P is a production rate. It's difficult to. There are literature where you say, I can dispose, I can throw away inventory. So there is a way to define a negative production, but it is a stretch. And so usually we want production to be non-negative, usually. And so if that's the case, then the production star T has to be max of this and 0. But this could be negative, in which case I would use the 0 production rate. That creates a lot of mathematical problems. Okay? So what we're going to do, we're going to assume
Excuse
that.
me, sir?
Go ahead.
Yeah, so could you go back to slide 5? Yeah, did you say that you put like C over 2 here, I mean by half, just for the calculation, easier calculation?
Yes.
Okay.
You can put that, you can call it a C, and then there'll be 1/2 everywhere else. That's okay.
Okay, thank you.
Yeah, it's just the way I do it. You can call H, basically, H is a coefficient of inventory cost, and C is the coefficient of production cost. It is not per unit production. You know what I mean? It is
Yes.
the cost of deviation. It's a cost from deviation.
Yeah, it makes sense. Thank you.
And how you find it is another story. But you can, for example, production, you can find a machine is rated like the car, if you drive a car on the road, then they say that the best fuel consumption happens at 40 miles an hour. But if you drive the car 40 miles an hour, then you lose time. So there's a cost of time, right? Because if you want to maximize the fuel, you would drive 40 miles an hour. But then if you're paying the wages to this guy who's delivering something somewhere, then you are paying him more because the same delivery will cost more at 40 miles an hour than at 60 miles an hour, right? And so the actual production, the actual speed of the car may not be at 40. Again, even though I have a P hat, which is the good production rate for the machine for whatever purposes, the machine may overheat, machine has a fuel consumption, all of those. But I also want to produce more. So in that case, the deviation may cost money. If you use less than that, then the machine is idle. The people who are handling the machine have to go home. So there's a cost of lowering the production rate as well. And so the Holt, Modigliani, and Muth Simon said that this is the ideal production rate, and that's if you deviate from this, because the objective function and the solution would ask you to deviate, then you will lose some money. And the same for inventory. Your warehouse has a certain inventory level, which is good for the warehouse. But if you put too much inventory, then the coordination problem becomes difficult. Accessing the inventory from places will be difficult. There'll be a crowding all over the place. There will be spoilage, which is more than usual, and that is not good. If you put the inventory less than the warehouse, then the warehouse rent is being used for inventory, which is not enough. And is also expensive, right? So there is some way of figuring out what is the optimal level of inventory for the inventory point of view, and what is the optimal level of production from the production point of view. But if you take both of them into account, then you may not stick with those levels. You may deviate from them because that's what needed. So if you want to go all the way, I'll show you what I mean by that. Suppose my demand goes like this. But this is too high. If I produce exactly equal to demand, then my demand has to follow the production demand like this, right? But you see the demand is very high and the cost of deviating from P hat is very high. And so my production actually may be going like this way. So the production is smoother than the demand. You see that? It costs less by being smooth. That's sort of what I mean by that. As far as optimal control problem is concerned, the quadratic problems are easy to solve. They are called linear quadratic problem, and that's why they actually use the quadratic formulation here. Other people have put the convex formulation, and they become more convex production planning. They become more difficult to solve, but there are optimal control papers on those. Kleindorfer and Lieber and all those people have done those, and these are cited in the book. Okay. So we're going to solve the problem in two parts. First, we're assuming that we will allow negative production. So we will not put 0. We will assume this to be the production rate, optimal production rate. Whatever it is, 0, negative, positive, doesn't matter. I also want to show to you that if my initial inventory is if my inventory is very large, sufficiently large, I mean more than sufficiently large, then this quantity could be negative. Because I have too much inventory, and the inventory is costing me too much money because of this cost. And so I want to reduce the inventory quickly. And the only way to reduce inventory quickly is to not just produce 0, but produce negative. So if the inventory is not very large, then this quantity will never become negative, and we are okay. Okay? And so just think of a problem where inventory is not very large, and then this will never happen, and we are going to be optimal. If inventory is very large, and that may happen, I will, at least from the control point of view, there's a solution to that problem, and that solution will come later in this chapter. Okay? So we're not just saying that we cannot solve the other problem. We can, but it makes it more difficult. So we solve the simpler problem first and a more complicated problem later. So simpler problem, we will not put 6.6. This is a remark. You see that it is not part of the continuation. The continuation begins from here. So 6.5, this is the remark, and then we continue to 6.7. So we put the optimal value of 6.5 in there, and we have I dot. And we have a lambda dot. So we have a 2-point boundary value problem. Here, I will give you another method of solving 2-point boundary value problem. So what I'm trying to say is that when you can solve explicitly, you have different methods to solve the problem. One was the reverse time construction, which we did in chapter 5. In a linear quadratic setting, we can do this, as we will see how that works. And you can solve those. You can solve. There is no. The people have solved the problems explicitly in many cases, but then there are differential equations that cannot be solved explicitly, and so in the end, you have to go numerical. For general cases, you have to go numerical, but for special cases, you can solve explicitly. And our literature likes explicit solution more than they like numerical solutions. If you look at the management science journal, you will see what I'm talking about. So to solve this problem, I take one more derivative of this guy, and I will have lambda dot when I take the derivative, and lambda dot I can substitute this value. So I have I double dot equal to that quantity, and then I substitute 6.8, I get this. I have S dot, but S is a given function. So I know what S dot is, okay? So now I have a second order differential equation. And that equation can be written this way. I put alpha as H by C. And that I double dot equation can be written this way. And this equation is a form which is second order linear equation. It is completely solvable. This is the right hand side, which is a function of time, and if it is 0, it's called homogeneous. Because of this, there's a way to solve this problem, and we're going to do that. So the standard method, which is described in Appendix A, there's an auxiliary equation for this. You put m squared for this, and m for this, and m for 0 for that, m to the 0, which is constant for that, and you get m squared minus rho m minus alpha squared equal to 0. This is called the auxiliary equation, and it's got two roots. One root is m1, one root is m2. You can sort of see that this is a negative root because this will be more than rho, so this rho minus more than rho. Never more than rho, but it could be negative, and this will certainly be positive regardless. But but those are the two roots. M1 is less than 0 because this is bigger than rho, and this was positive, so M2 is bigger than 0. And general solution of this equation is A1 e to the m1t, a to the e m2 root t. If this was 0, if this right-hand side was 0, we will stop there. But because right-hand side has something, we will call a qt, which is called the particular integral. And there are formulas for given functions here, at least for a large number of functions given here. You can find books that will tell you what the qt should be. Obviously, any integral, particular integral, can include such terms as well. But that, why do include those terms? Because we can include those terms here anyway. So any particular integral that does not include these terms is called special particular integral, and we'll only use special particular integral. Once again, you are not learning differential equation theory. We are just giving you how to solve these equations by a recipe and go with that. So a second order differential equation has two boundary conditions. One is going to be A1 and one is A2. Notice we need two boundary conditions as well if you have this equation, because we have I0 and a 0, and those are the boundary conditions. And we can solve the problem with those two boundary conditions. As you know, there was a 2-point boundary value problem. And it's a 2-point boundary value problem with two conditions, and it can solve it. So when we change this problem into a second order equation, of course, the second order equation will have two constants. Remember, there will be two constants here as well. One is for it at time t, and one is lambda at 0. And those values are not known to us. And once we know those values, so you can see that there's the same situation here. We will need to find out the two constants. And two constants will be found by substituting these two equations. So let's go with that. So we now have IT equation and a lambda t equation, and we can solve. So there were two equations now. This when you put t equal to 0, this becomes I0. And we put t equal to 0, this t equal to capital T, this becomes 0. And then we have two equations in A1 and A2. We have two equations and two constants. Hopefully we can solve them. So that's what we're going to do. But Thompson and I decided that we will do more than that. So we'll try to get some more insights, because after all, this was not a math paper, it was a management science paper. And so we said, let's go further. And so this is what we're going to do now. We define the two constants, and we also define these two terms, B1 and B2. When you write papers, and then you will find out that in order to express certain things, because these things appear so many times, you decide to write them as this, and then you make it easier for yourself. So when we impose all of these things and we solve those boundary conditions, we find, so we solve these two equations for A1 and A2, which are algebraic equations. You can easily solve them. And when you solve them, you find A1 and A2. So I have A1 and A2 given by these formulas. And so the problem is, in some sense, completely solved. Because I have A1, A2, I have, once I put A1, A2, I go I2, and once I know lambda t, and once I know lambda t, I know p star t. So the problem, mathematically, the problem is solved. No contribution here, because this is just the standard application of linear quadratic formulation in control theory, and we are done. What is important now is the rest of it. Okay, so the rest of it is further analysis of what we can say more than what we already know. So M1 is negative and M2 is positive, and assume T is sufficiently large so that these guys are negligible. Because when T is large, this is very small. When T is very large, this is very small. And so in some sense, for very large T, sufficiently large here has a different meaning. It basically says large enough so that you can tolerate this negligible aspect. It's up to you in some sense. So if I tell you that 0.0001 is low enough, then you can tell you what the large value is. Okay, that's basically what it is. It doesn't have the same notion of sufficiently large T as in the previous chapter. So in those conditions, A1, so you see, I can change this to 0. I can change this to 0 in those two formulas. When I do that, I get this. But I don't want to make this 0. It's also 0. It's also negligible, because M2 is positive and minus M2 is negative. So that can also disappear. The reason I don't do it, because M2, if you look at it, there is a if you look at it, there's another term going on with it. Is B2, what is B2? B2 e to the minus M2, B2 e to the minus M2t. Let me see, A2, B2, B2 divided by M2. We made this 0, we made this 0, so it becomes B2 M2 divided by e to the minus MT. But you will see later on that we will have another term that goes with it, which I will show you. We will have a T minus T term. And so when T is large, and when I go to small t, someday the T is going to approach to capital T. And that formula will show up in B2. That's why I will keep this term in there. So my approximation is given by these guys. I will call 3 parts. So I break these guys. I break this solution into 3 parts. First part is this part. Second part is this part. And the third part is this part. Production, the same thing. Lambda, the same thing. So these terms I will put an ending correction because they are when small t is very close to capital T. And this is what is called a turnpike, which I will say a little bit more briefly. And this is the starting correction when I'm not on the turnpike. Okay. So note that if B1 equal to 0, B1 is the value coming from here. If B1 is 0, it means I0 equal to Q0. So you can sort of see that if P1 equal to 0, this guy becomes 0. And I0, Q0 is this guy is Q0. So the Q0 is a value on the turnpike. Why call it a turnpike? Think about a freeway. And on the freeway, you are, let's say, going to somebody who lives in Fort Worth. So a friend lives in Fort Worth, you live around here. And so what you do, you are going to take a service road, not service road, you're going to take a ramp, and you take the ramp and go into 635. And then 635, you stay for a long, long time until you take an exit, and then you go to your friend's house. So the initial ramp is a starting correction. Ending ramp is an ending correction because you have to go to your friend's house. In between, you stay on the turnpike. And now what happens is if there is no friend and time is infinity, then you will stay on the turnpike forever. Right? So economic theories are infinite horizon theories, and they tell you that I have a capital which is not enough or too much, and I will change the capital so that the capital is now on the turnpike. And then if it's on the turnpike, I will stay on the turnpike forever. And that's called the growth theories in economics called turnpike theories. And there are lots and lots of literature on that. And if B2 is 0, then ending correction vanishes. So B2 is 0 is same as your friend lives right on the turnpike. It lives right on the turnpike, then you don't need an exit ramp. You just stop and see your friend, okay? So that's sort of the analogy as much as I can tell you what's going on here. It's also important to say the solution makes sense, and when you have rho equal to or bigger than infinity, one can then show that in this case, there are no pathologies as long as the sales rate does not grow too fast. So as long as the sales rate have reasonable regular function, you are okay. So t going to infinity, the ending correction goes to 0. And so lambda t is given by this. Also, we like this. So we would like this to go slower asymptotically. And this is easy to take for any ST for which a QT is known. So we are not going beyond that. We think that we can do that. And by sufficiency of the maximum principle, we can, because maximum principle sufficient, we can show that this control is now sufficient, optimal. And if I0 is Q0, the solution is also the turnpike, and this is your turnpike. We already gave you a notion called optimal long-run stationary equilibrium in chapter 3, and this is the triple if there's no control constraint, because control constraint P bigger than 0 was removed. We did not put that constraint. We used 6.5 instead. And so without that constraint, it's a triple, not a quadruple. And this is our turnpike. So what Thompson and Sethi wanted to show is that we can do a little bit more work on this and give you some ideas of what the solutions look like. By the way, we will have more turnpike theories in chapter 7, and you will learn a little bit more about them. But until then, we will see what we can do while we are in this chapter. So let's solve some problems. Here's a demand. And here's a demand, then this is the 2pth derivative Now that's a polynomial degree of 2p, t to the power 2p. This is t to the power 2p minus 1. So it's a general polynomial demand. And for that, you can see it's Fillinger or whatever, and you'll see the 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 the, the, the special particular integral is given by this, where this is the first derivative of s, this is the third derivative of s, and so forth. If demand is sinusoidal plus some kind of a given by this, and then you can see that the qt is given by this. So there are some given in appendix. You can see some of these things. So we solve one problem where st is given by this polynomial. We already know what qt should be, and we also know q dot should be, and so we can solve the problem like this. You can see these quantities are going to become 0, st goes to infinity, small t goes to infinity. So you can see now what is happening. We have a demand that is sinusoidal, goes like this. And the production begins at 30. No, production begins at around 49. And it goes like this. And eventually production goes like this and goes back to somewhere around 29. And the inventory, as you can see, is going like that. I want to show something what is going on here, and let's continue. Now I want to change the I0 to 50. So initially my initial inventory was the initial inventory was 10. So the 10, and it eventually went to 29 because it was too low. The demand is higher than that, and so I had to build up the inventory by using some production, and I did that. But I didn't use production exactly close to demand, but I did use production which was to build the inventory. When the demand was low, the production built the inventory. When the demand was high, the inventory went down because I have to satisfy the demand. Now I put inventory 50. Well, I put inventory 50, then my production goes way low, and my inventory then goes down, and eventually it goes to 29. Now let's assume that the inventory is 30. We remember Q0 was 30, I think. What is Q0? Q0 was, where's Q0? Q0, this is 0, this is 0. Q0 is 53. Q0 is 53, okay. So I have 50 large starting inventory. Then I have a inventory that is around 30. And you can see the inventory actually goes like this. You can see the production is going like this. And we are going to 20. Now, what you saw is that even though I started an inventory at 3 different levels, I started inventory at 10, then at 50, and then at 30. And in all 3 cases, somehow or the other, the eventually production rate after 8 periods went to 29. You can see now that as time goes to 0, time goes to infinity, you are getting into some kind of a stationary kind of a solution. It's not stationary in terms of time, but it's a stationary in terms of its nature. If time is infinity, the solution kind of sticks around in a similar way. So at some point, once this is 29, you see, if the 29 is here, so if I started with, so it's almost getting close to 29, and so regardless where I start, this cycle that you see inventory will repeat. So this cycle will go like this, again it will go like this, again it will go like, it will repeat in almost a symmetric fashion. So that's what's happening. It's getting to the turnpike. there is an inventory infinite horizon solution, and that solution begins with with I bar, Q bar. Let me see. Yeah, see Q dot plus S. So the P bar, so the I bar is Q, and P bar is Q dot plus S, and so you will have the. I have a question right now. Just 1 second. Well, this is okay. I'm sorry. This is the 8-period solution. We don't have the infinite horizon solution here because we are solving the 8-period solution. All we're trying to show here is that somehow the inventory is turning to do this. But if you have infinite horizon solution, you can sort of see if you have infinite horizon solution, and if you started with the inventory, it will sort of go like this. Okay. I need to go to the next one. If you have a more complicated, let me see now. Where is my sofa? Okay. If we have a demand which is also growing this way and a sinusoidal component, and there's a drift to that, upward drift to it, again there is a integral that's available to us, so we can solve this problem for any kind of S. This is another way to show something which is very important in the production planning literature called linear decision rule. That's also given by the HMMS model, which is well-known model in the literature. And the two-point boundary value problem given by 6.7 is a linear system differential equation. And there is another way to solve that. And that solution is given this way. So let me just quickly go through it. I'm not expecting you to derive this thing on your own. This is simple if you knew the differential equation theory. Otherwise, you just have to look at what it is. So lambda t can be written in this way. So you can see lambda t is kind of linear in IT. And so the production will also be linear in IT. And you need to solve this equation by knowing psi t and st. And differentiating 6.3.2, substituting for I dot and lambda dot, and we obtain this equation. And the above relation must hold for any value of initial inventory I0, which means that this quantity has to be 0, this quantity has to be 0, and this quantity has to be 0. And so the S dot is equal to SC squared minus H. This is given from here. And the psi dot, which is this quantity, has to be equal to 0. So psi dot is given by this quantity. So and because lambda t is 0, we also know that you put the value t in there. We also know that this quantity must hold. And so because this quantity must hold, then again, regardless of value of IT, to hold this quantity, we have to have these quantities equal to 0. So now what we are doing is solving this equation and this equation with these two boundary conditions. And this, by the way, is called the Riccati equation, which has a standard solution in the literature. And the solution is given by these guys. And we have a P star T, which is given in terms of this. And you can see that the P star T is linear in I star T. There is a coefficient, and there's a linear one. And so this is called the linear decision rule. This particular discussion comes from a book that Ben Susan wrote, because they use control theory instead of the Modigliani and Muth Simon, who also came up with the decision rule but did not come with the explicit formula, whereas Ben Susan book has an explicit formula given a solution of this Riccati equation. Let me see whether we have a time. We have time, so we will cover part of chapter 6. We will not go to 6.2, but we will cover this part. And then we will talk briefly about the exam. So let's continue here. When t equal to infinity, I want to assume rho to be bigger than 0. And I want to solve the problem now by going back to 6.5. So what I want to do now is to show you that I don't want to simplify the problem now. I would allow you to have 0 production. So I would like to use this formula. So I'm not allowing negative production, but the constraint is going to be active. If my initial inventory is very large, the constraint will be active, and I want to find out how to solve this problem. That problem is no longer a Riccati problem, so it is not possible to use the linear quadratic theory. I have to use the maximum principle. Okay, so I have to use maximum principle here as well, but the solution to get to linear quadratic equation, I must assume that there is no such constraint. So I'm not going to put the constraint. Yeah. So we're going back to the formulation that we started with, and we are substituting t equal to infinity, rho bigger than 0. We are substituting s to be a constant. So s dot is 0, s is a positive constant. We can do all of that, and we can finally come down to a solution. We can find the value of b1, we can find the value of b2, we know q dot equal to 0, we have a particular integral, so we can actually solve the problem without the non-negative production. And we have a turnpike. In the turnpike, we have no inventory changing, no lambda changing, but P bar is given by this, which is exactly equal to S. So we are producing exactly equal to demand at the turnpike. So the inventory stays 0, and we produce exactly up to the demand. But if inventory is not 0, I have to eventually bring it to 0 somehow or the other, right? And then produce along to demand. But how I bring it to 0 is a transient solution, and that may require P equal to 0 if inventory is very large, and P equal to 0 was not allowed. P equal to 0 was not allowed if P was negative. We allowed P negative in the previous problem, but now we don't allow P negative. But we can put P equal to 0 at that time. So that requires some work. So let's solve this problem in 3 cases. If I0 equal to Q, the optimal state on turnpike, we're done. If I0 is not equal to Q, we have some cases. One is I0 less than Q. One is I0 between these quantities, and one is I0 above these quantities. We need to solve all of those 3 problems. Why I come to this one will become clear to you. It's sometimes you first solve the problem, find out various cases, and then you begin with these cases as it is. So let's take the I0 less than Q, and then B1 is I0 minus Q0. P start is given, I start is given, And so we are done. In order to look at this, I want to give you a picture first. And I think that picture gives you a slightly better understanding of what's going on. So let's go to a picture. So here's the I0 equal to Q. This is my turnpike. If I had this initial Q, which is going to be exactly equal to 7.56, 7.56, 7.60 in this case. And this is the picture drawn for these guys. And then I will just stick around along there. If I0 equal to Q. But I0 can have three cases. One is I0 less than Q. Well, if I0 is less than Q, I will produce exactly S. And asymptotically, I will approach this turnpike. I will never get there, but asymptotically I approach turnpike, and this is my optimal solution. But there is no other. I want to be, there's a, in the next lecture, in marketing, I will give you another more general setting in which I will show you that the optimal solution is to be staying as close to the turnpike as possible. But if you stay as close to the turnpike as possible, this is the optimal way to do it. No other way you can do better than this. Okay, so this is basically what's going on. If I0 is not too large, and the too large is given by this number here. So if it's between this quantity, you will see that I will have a P star equal to P hat plus lambda by C. And no, I'm sorry. I have a P star equal to P hat lambda by C. This is where the P star equal to S, and I will eventually it will get to S, but is asymptotically going there. Same here. So in this case, that quantity is bigger than 0, and so the previous solution is still good. But what if my inventory is above this guy? The inventory is above this guy, I will find that my P star plus lambda C is less than 0. And if it's less than 0, then for a while, I should use P star equal to 0. And at some point, I will go to switch this quantity. And I need to find out this point T hat, where I made the switch. And then find out whether the optimal solution is satisfied, maximum principal is satisfied on this side and on this side. So that's the idea here. You can sort of see now that only when inventory is very high, I have to resort to P star equal to 0, and I have to find out the value, this value at which the solution switches to the solution in the previous case, where I don't have to worry about the constraint. So we are going to continue here. So we can easily see from 6.40, this is where we are going there, that P star 0 is bigger than 0 for this case. And also P star dot is bigger than 0, so the control, therefore the optimal production rate is once again given by 6.40, and we have I star T coincide with I star T Q monotonically as T goes to infinity. Concluded I star T approaches Q monotonically, not coincides with, and T goes to infinity as shown in figure 6.4. So those two cases are done. Case 3 is the case that's more complicated. I have I0 is bigger than this, would have a negative value P0, which is feasible. So if I go to 6.40 and I put this value, I0 bigger than Q minus S1, then then I will see that because M1 is negative, I will see that this quantity will become negative. I mean, P star T, I'm sorry, P star T will become negative in case 3, and it becomes 0 exactly at this quantity. So that's how I got this value Q by S1 here. So it becomes exactly 0 at this quantity. So it's clear that for I0 bigger than Q, I must resort to negative control in the previous setting and 0 control now. And if I put 0 control, then I have to redo the maximum principle. Okay, so that's basically where this quantity comes in. And the only thing is that we now got the solution. We only have to, the solution comes intuitively. What we need to do is to prove that the maximum principle is satisfied. When the maximum principle is satisfied, we will know what the lambda and P and inventory is here. And so we can easily find out the path and see the Hamiltonian is maximized, which is true on this side. But we also need to know if the Hamiltonian is maximized on this side. So we need to find out the values of the trajectory on this path. But we can do that. We have all the solution, all the things we want. And that's the next thing we do here. So by 6.6, which says I cannot use negative value of P value, so I must set P star equal to 0. So I already gave you the figure, 6.4. The time T hat is exactly the time when this P star, this guy becomes 0. So if you go to 6.40, we will see that I0 equal to this, P star equals 0. And so I star T hat is exactly Q minus S my M. So what I'm going to do is I'm going to show you that if I'm here, then that control 0 will reduce I0. At some point, I will become exactly this, at which I can switch back to the ordinary solution. Because then I don't need to constrain P star bigger than 0, because it's already 0 and it's going to be bigger than 0 here anyway. So I know exactly the T hat, because I can easily find out the T hat. So I can find out the T hat, and at T hat, I can find out all the values that I need for the dual, the shadow price, lambda, as well as all that. So that's what I'm going to do now. So the adjoint equation in this interval now is lambda dot is what that are, and lambda T hat is exactly minus CP hat from this business. Lambda T hat is exactly C times P hat, so this becomes minus CP hat. So I have now, I can substitute I0 minus ST for I in equation 6.4. I can substitute that. And I can solve for lambda. Because lambda is now a single equation. I is already solved. I can solve this, which gives me the lambda all the way from T hat to 0. Okay? And we can easily obtain T hat. We can also get lambda hat. And then this is my lambda. This is my lambda dot. And there's a lot of things going on, but eventually I can find the lambda T. And I can give you, so what's going on here? Let me see. Yeah, okay. So the maximum principle is Hamiltonian condition is simply satisfied because all along that trajectory, the control will be less than 0, but P star bigger than 0 will force me to put P star equal to 0. So maximum principle is satisfied. But for that, we need to have the lambda, and lambda gives me the Hamiltonian. Hamiltonian gives me the first order condition will give me P star less than 0. And because the constraint, I will set it to 0. So the 0 is the maximum along this path. And so we're done. So it requires a little bit of an intuition by this figure, but we can solve the problem that way. I think we're gonna talk a little bit about the exam. So the exam is next week, and it will be in class, and Gautam is going to proctor the exam in class. Is that okay with you guys?
Yes, Professor.
Okay. The other thing I want to know is I can cover the exam up to this point in chapter 6. That means don't include the V trading model, but include up to this point. Because the reason I could also not include the chapter 6, but then the chapter 6 will be included, all of it, in the next final. So final will have too many chapters. So if you guys are willing to cover all the way until this point, that means the final will begin from here and the midterm will close to this point. That's one possibility. Or we can have the midterm only up to chapter 5 and the entire chapter 6 will be in the final. Any thoughts on that? Because I need to come up with the questions.
Can we have it till chapter 5 if others agree? Yeah, Katalia, you were saying something.
You want up to chapter 5?
Yeah, yes, Professor. Like, let others say, but like, yeah, Katalia, you were saying something.
Let me find out what the other people are saying.
Yeah, sure, Professor. Yeah.
Can other people tell me what's going on?
I also prefer up to chapter 5 only.
What about the other two?
Same here.
Yeah,
Okay.
me too.
Okay, so we will do exam until chapter 5, and we'll do 6 all the way to chapter 13 in final. So that's one part. What else? Let's see now. The other thing is, let me see. The exam will be at the same time, and Gautam will proctor it. Okay, so he knows that. The last homework was 5.2, 5.4, and 6.1, right?
Yes.
Okay, so my tendency is usually not to give you a homework because the homework will cover 6 and you're going to prepare for the exam, so you don't want to bother with the 6 right now, right? So I will give you the homework that will due 1 week after the exam. It's okay?
Yes, Professor. Yeah.
So the homework that's going to be due 1 week after the exam is 6.14, 6.19, and 7.7. That's due on, the exam is March 10. That's going to be due on March 17, okay?
It's spring break, Professor.
Huh?
Next week, the following week after the exam, it's spring break.
Oh, it's a spring week. Let me see. Oh, but you don't want to do 6 and turn it in exam. So it will be due on March 24, right?
Yes.
Yeah. So the homework 6.14, 6.19, 7.7 is due on March 24. And the exam is going to be on March 10, and it will cover from chapter 1 to 5. There will be 4 questions. There will be 4 questions. You will be required to have one sheet of formulas with you. It should be only on one page, not on both sides. It will be the standard A4 page that we have. You can write whatever formulas, maximum principle, whatever you want to write. And Gautam will go over this, and you will turn in the exam to him. You will also turn in on your formula sheet to him, and he will bring you the paper. You're not allowed to have a cell phone with you, but you are allowed to just have that one formula sheet with you. Is that understood?
Yes.
Is
Okay.
it 2 pages? I mean, double-sided or just one-sided formula sheet?
The one sheet only on one side. The other side is blank.
Okay, thank you.
Yeah. I think I have found out that more formulas you put, it's become a negative return. At some point, you look at too many formulas going this side, that side, you lose so much time that you never finish the exam. So I found, I remember my PhD exam at Carnegie Mellon, they allowed every book you can take with you. And so I've seen students who took 10 books with them. And every time there was a question, they go through every one of these books to see if the solution was there in one of those books. And they never finished the exam. I hardly ever took any book, and I was actually one of the best qualifying exam person at Carnegie Mellon for some reason or another. So I basically tell you that try to remember more, practice the questions that you did not do. The questions would be either from the book or similar to what is in the book, because there may be different numbers. It may be similar question, but I may change numbers on you, kind of thing. But if you solve many of the ones that are not assigned to you, you can solve those problems, then that will prepare you a lot. And if you remember some of the formulas that are not complicated ones, you should remember them, and because then you can just quickly use them without worrying about where they are. Because one of the things you do by putting the formula on the formula sheet is your mind doesn't want to remember them. And then every little formula you look at the sheet, and every time you look at the sheet, you have to look at, it's not alphabetically arranged, so you find out where the formula is. Like looking at a password. Every time I look at my password, I spend more time because I don't know where they are. They're not alphabetically arranged. Each time I have to go through the whole sheet again. In any case, you spend a lot of time looking at these sheets. So make a very clear sheet. Don't make it so that it looks like a bird has walked over the sheet and you have to have a magnifying glass to look at the formula. My sense would be to have a clear sheet with formula that are essentially needed, and then remember some of the ones that you have in your head. And that I've seen a lot of people don't finish the exam. There are 4 questions, everybody is in the same boat. And if you finish 3, you're just going to suffer. Those who finish all 4 are better off, and those who finish all 4 correctly are obviously much better off. So with those warnings and remarks, I wish you good luck. And I will set my exam with Gautam, and he will proctor the exam. Anything other that you have, send an email. Feel free to send me an email if you're not clear to you. Okay.
Perfect. Thank you.
Okay.
Thank you.
Yeah, we'll see you then on 24th. That's almost